möchte heute einen Exkurs machen in den.
I'm going to take a detour to there's level 4. So, as I said, what happens, well, in the cities, in urban driving. And if you look at this video here, or this animation rather, it is much more complex than the complexity in the other levels, highway, level 3, for example, which is why we use a set of sensors which is far more complex. Now, in the field of highways, around 15 sensors, whereas in urban contexts, and in particular when we move to level 4 applications, the number of sensors increases sharply. So 40, as many as 40 and even more sensors based on 4 different physical sensor systems. This is in order to capture the full complexity of urban road situations and to do this safely. Well, basically, we're talking about a whole new generation of sensors simply because the requirements are so much more demanding. For example, resolution, for example, in order to really fully understand urban situations.
Besonders wesentlich, auch das haben wir heute schon diskutiert.
As we'd already said today, the central ECU, when it comes to that, requirements are very, very high. And we have to draw a distinction between what you want to use in privately used cars, because there are, on the other hand, these very demanding cost targets. And then there are also those cases which have to be more open for future requirements, which have to use far more powerful algorithms, for example, or at least have to provide for this possibility. So central ECU, and not to forget vehicle positioning. So these types of sensors, we will have to use them as well.
Und der Matthew Avery in der JEDAS-Konferenz in Essen vor 2 oder 3 Wochen hat es für mich auf einen sehr guten Punkt gebracht.
Actually, at a conference 3 weeks ago, somebody said, it was the Thatham Research Association, the umbrella association of British insurers, they said the vehicle will have to be able to cope with all situations that we can reasonably expect to come up. Now, this doesn't seem to be, well, a very clear definition, but it gives you some sort of guideline that we really have to control what happens on the roads. We have to know what the road situations are like or can be like, and we have to be reasonably certain that the vehicle will be able to cope with these situations, including such things as degradation, also in order to be able to perform minimum risk maneuvers, of course.
Dann die Sensoren entweder simulieren oder emulieren.
Then you simulate or emulate sensors. That's another thing we can do. And then the trajectory will have to be determined, and all of this will have to be in a simulated environment, be tested. And by introducing different behavioral models of other road users, in a closed-loop simulation, you can then calculate different variations. In other words, in your environment, you need to have your context, you need to have a behavioral model of those other road users or vehicles, and because of that, I can then test my system in this closed-loop system. So the vehicle will move in this closed environment like it would on the road. Of course, it depends, on the quality of simulation, really. So whether it's driving dynamics, for example, or the behavioral models, so how well that can actually be captured. The question is, how well can you show that in your simulation? And perhaps just as an aside, that too comes from this ADAS conference 3 weeks ago. Now, all the registering authorities, which is mostly NIS, but also the European Commission, of course, for them, this is one of the tools, really, when it comes to highly automated driving, really, which is why it's so important to the, authorities how these simulations were carried out. And the EU Commission said, well, actually, they would like to carry out their own tests even. So from the point of view of the regulator, if they carry out a type approval, for example, to really gain some insight into how valid the application actually is. And now this, however, comes with a great opportunity, namely because we can abstract the simulation of a vehicle by using multiple instances in what we called a backend earlier. We can carry it out with a high degree of parallelism. So the number of hours, of miles, of variations that we can actually test can be increased by leaps and bounds by parallelizing your computer infrastructure. And that is, of course, precisely what must be done. Nevertheless, we will have to select, well, some points which we'll test. So individual points. We cannot test all the combinations, even if we've set up an optimal system. So I've got a quote here from a system safety conference which was held in the US this year. About stable and unstable system states and how these can be detected. So in the left, you can see a quite straightforward example, of course. It can easily get more complex. So you have a lot of traffic, and there are two parameters. And there are some areas, and I think it's easily understood. There are certain areas where you're very robust. If you drive out soon enough, or if you wait for the other system to emerge first, here from the road, the risk that your vehicle will happen in this context is really very small. What's more interesting is what happens in between, where the system will have to take decisions which, in a critical traffic situation, could get too close to the limits and are highly critical. And what this tells us is that the test, of course, should really concentrate on what happens at the limits, the lines on the graph on the right. So if you know it's unsafe, then you will not, of course, drive around the corner. But it's the limits and what happens at the limits which is interesting. And I think the great opportunity that comes with these kinds of virtual tests is that you can define these areas. You can really select the area where in the virtual test, but also later on during validation of your simulation, you will really have to focus on.
Die Validierungsaufgabe wird natürlich nicht verschwinden. Das heißt, auch wenn ich sehr viel
Of course, complexity won't go away. So even if you've got a lot of your scenarios and you've got them into your virtual simulation world, the question will remain whether this really is a true picture of reality. So what you've got in your computer network, what you've tested in your virtual environment, will that really be the same as what I can expect to happen later on in reality? So you'll still have to, also have component testing, combination testing, and also the driver, of course, will never disappear fully. Because we cannot, of course, come up with a 100% solution. But at least I can, make progress step by step. And at the first level, I'll look at the ECU architecture. And of course, it's about testing embedded systems. And it's about timing, network utilization. And in the second step, we'll also have to test against the vehicle. Now, again, of course, if I have to test all the features again against the road, of course, then I would have made no progress. And that is why I believe here too, if we use the robust points inside the outer inner feature space, that can help me in order to really see what happens in this area between robust and not robust. But of course, you'll have to use your tool chain. In other areas, of course, you can do this, well, not so regularly anymore, using regression tests, for example. In other words, I call this robustness-guided testing. And I believe it is an important tool to move from generic validation to a more targeted testing approach.
Wenn jetzt jeder OEM weltweit Millionen
Well, if every OEM around the world ran up millions of miles, then of course that would be a big economic waste, right? So,
ökonomische Lösung finden.
do you see any likelihood that we'll find a better solution? OEMs teaming up to create joint data sets. I mean, would that be desirable, first of all? So, how do you see this? Well, I think it's very important. It's necessary even. And for highway, with the project Pegasus, they're already doing it. And I think we'll have to do exactly the same for urban driving assignments. I think it's an absolute must. Nevertheless, if you don't mind me continuing here, even then, you will still have a lot of driving to do, because it's this combination of the context and the system which you will never get from a database. So that will have to be validated separately.
Heute möchte ich Sie
However, today I should like to take you on board from ADAS to AD, enabling the disruption.
Ich möchte mal dieses Dreieck
Let me look at the triangle of driver, technology, and business case. The discussion is always very engineering-driven and technically driven, in particular in Germany. But the question is, what are we doing this for? I mean, there's a mission behind this. What is the promise of automated driving, and where's the money coming from to get it in place?
Aber wir dürfen den Fahrer nicht vergessen.
When it comes to driving, we mustn't forget what would the driver actually have at the end. What does he want or she want? He or she wants to have the time to do what they were intending to do, and they do not want to be kept busy more with monitoring driver assist systems as compared to the original job of driving the car.
Soweit zur User Experience. Jetzt zum Business Case. Ich glaube, es ist relativ klar, hier eine Staukarte brauchen.
Okay, that's a traffic jam map. If you look at your own car, when you're getting here, how many people are on the road? To the left, typically speaking, 1.5 people per vehicle, per car. This is at least, there's room at least for 2.5 more people on board. So we looked at the capacity of the vehicles. We have the need to reduce traffic jams. So this has to be brought together somehow. And what do we see? Indeed, mobility services are coming up everywhere now, which are trying, by way of new electronic media, to service this very market, supply and demand.
Dritter Fall noch, hier also Safety, den ich jetzt als letztes.
Okay, and that's the safety issue here, impact to traffic safety. And you can see the different mileage vis-à-vis the number of traffic fatalities and what we have to prevent them. We have seat belts, we have ABS, airbags, ESC, ADAS, etc. And we are hoping to be able to believe this promise that in the future, when cars are driving autonomously, this number of fatalities will go down.
Und so geht's weiter. Und genau das werden die.
And it goes on like this. And this is what customers will expect from cars, from mobility service. They want a mobility service in their calendars. You know, when's the last meeting end? When's the next one start? I want 3 proposals. How do I get there the fastest, at the lowest cost, and in the most secure and safe way?
Ich habe hier 32 Zahlen, aber
I have 32 sensors here for an autonomous vehicle. In the previous presentation, they were talking about 40, so that's the order of magnitude. And the question is, where are we? Initially, there was a sensor driven by a function, ultrasonic sensors, etc. Now we see that one sensor can support several functions, or one function can actually supply itself with information from one and single sensor. And then we have vehicles which can actually synthesize the environmental model, just like an app. And after this, even if the vehicle comes from the outside, like Tesla has done it with the 7.0 to 7.1 update, that then at the point in time when the car was developed, didn't exist at the time. This update actually made it possible to improve that situation for Tesla. We have to understand this. Now, what does it all mean? What can this vehicle do? This vehicle has such a good perception of the environment that it is not just an ego vehicle and can assess the situation for itself, but in the environment, it can also look at different other participants in the traffic and see when there's a collision ahead. It can actually respond to this, stop the car safely. A little bit of problems with, or the challenge for the sensors. We are producing data in the range of megabyte per second, and in the case of doubt, we need one bit that tells us brake or no brake, and we have to find this in this enormous amount of data, and correspondingly, we have to be very careful when we are developing all this. This has been addressed by Dr. Krumme in the previous presentation as well. The question is, how is this environmental model then projected in the technical architecture onto the vehicle? And what I would imagine here is, for example, this is a centralized system like it is in the classical car development situation. Think of ESP systems. It was centralized. We had an NVIDIA, Texas Instruments, and other platforms that can be used. And over time, then the cross-down effect happens. That is to say, the whole thing is distributed. The logic is distributed. You have lots of different ECUs, and you stepwise arrive at the cost minimum in producing them. But when it comes to the suppliers and for the semiconductor manufacturers behind them, it's not a problem to develop sensors and have 16, 32, 256 additional gigabytes to be burnt onto the chip and have the logic system run. So we're observing at the moment that here, this is the very spot where the war breaks out, because if you control the environment, then you control the architecture. And it's highly interesting to see whether this will remain with the OEMs or whether the suppliers will grab control of this environmental field.
Die Umfeldabstraktion ist der kritische Punkt, und wer das Zepter darüber behält.
So the environment, this is the critical point, and who is in control of the environment will be king, so to speak, because they can then say, okay, you'll get 60% or 80% at the price of 2,000 euro with this sensor set, and you get 90% for 2,000 euro and for a different set of sensors, etc. And if you know what's the maximum that you can that you want to spend, you have the maximum spread there.
If we don't have a safety focus, we will not be able to succeed to deliver this to our customers. They will claim or they will ask us if this is safe, and we need to be really sure that we can prove it. But then, as some of you have touched upon, I think we need to be guided by some proven in use target values in order to achieve the final verification. So it all boils down at the end to verification. We need to provide the evidence of the achieved functional safety, and we need to be able to argue that our safety goals are complete, correct, and complied with. If we cannot do that, we will not be able to launch it to the customers. We think that we need to chop the elephant and try working with a bottom-up approach where we look at the different building blocks of your complete system, try to isolate them as much as possible, and find methods of verifying the different parts one by one. I think that's the only way actually forward. But then, for sure, we need to drive vehicles as well. So we need to combine this bottom-up approach with vehicle driving and collecting data. And it will be significant amounts of data for sure, even though we will not achieve the complete verification just based on data, we will need to collect a lot of data together. And I think being an OEM, we should be able to have cars running, quite a few of them. And as someone said, we could probably work together with other OEMs and gather data jointly. What I think is important here is to try to focus the data on challenging scenarios, because just having lots and lots of data of the same kind where everything works fine, that's not challenging. I mean, we had the discussion or a slide previously about finding the boundary conditions, and that's where we should focus our data collection. This is a schematic, but we look at redundancy in every sense. It's redundant sensing, redundant sensor fusion, so the perception part of the system is redundant. We need to have redundant decision making, and then redundancy on the actuator side, mainly braking and steering, but potentially also engine control. Finally, there is one really important task for the vehicle platform, and that is to ensure that the vehicle can always stop safely, that the system is fail operational. Okay, so finally, in summary, I think safety, or we think at Volvo, that safety shapes and holds together the building blocks enabling unsupervised autonomous driving. A thought-through verification strategy is needed, and we try to work with a design for verification mindset. We need to make sure that the vehicle platform is capable of performing a blind safe stop. The perception system, the compute platform, and so on must be able to handle deep learning, and I don't think anyone could define it up front. We need to make that an iterative process. You need to dare to change during your development cycle. And for sure, cloud connection is a key for accurate localization and to have a centralized HD map.